But it's not the only kind of independence. And again, psychologists often got this confused. So this is an example of that notion of the probability of getting both the horizontal and the vertical stimulus as the product of getting them separately, so-called marginal probabilities. But there are other kinds of independence, and we tried to choose a terminology that was not the same for so confusable, at least in talking about them. And one of the really super important ones, and one that has been called independence by some investigators, including the psychologist Garner, really is not independence, it's a type of invariance. So it means that the probability, for example, as an example, of getting the feature A, given you were shown the stimulus SI, is the same of reporting A, given it was in a different stimulus. Okay, so you can see that's not independence, that's just a type of invariance that if whether the feature, say the horizontal feature is an E or an F or a square A, if this property holds, then it won't matter. The probability of getting it will be the same. Cross-feature invariance, very strong assumption. This was sometimes made in the models, but nobody ever thought it was really going to be true because it would mean that the probability that you perceive a horizontal line is the same as the probability of perceiving a vertical line, it's the same as so forth and so on, even within a stimulus. So this is a within stimulus type of invariance. And all of these are, again, of course, logically separate. One of the other strong assumptions that was usually not explicitly mentioned was no ghost features allowed. We call these ghost features because nobody's model allowed for these things, and basically they're false alarms. They're saying there was a feature there when there really was no feature there. And again, the models do not permit that. You could lose features, but you could never gain them falsely. Okay. Well, when we went and did our own experiments and got other people's data, we found out that none of those assumptions were true. They were all falsified. Now, unfortunately, the research kind of stopped in this area because once we had learned something, we could have presumably built more complex and truthful models and found out more about the observer. And whether people were discouraged by these kind of results or they just were going on to new fads, I don't know. But it was kind of a shame in a way. But it was already showing that there's so much configurality, even in letter perception or perception in most simple kinds of alphabets, that you have to take them seriously. You have to build configurality into your theory or model. So here are some of the specifics in terms of what we call macro analyses. We could not only look to see if the probability of reporting A was invariant, whether A was in one letter or a different letter. Okay, we could also do a signal detection analysis and see if the sensitivity was invariant. Okay, so if your sensitivity, hopefully most people have been in class where D prime means signal to noise ratio or the separation of your two distributions. So you could test at the sensory level whether the sensory perception of the horizontal line was the same in the different letters. Okay. Furthermore, you could look at the biases too, known as beta in signal detection theory, to see if the bias changed. But the most important was the sensitivity. Now, microanalyses have come under some threat from some of my former students, and for good reason, because they're a little more chancy in terms of some very, very strong assumptions have to be made to use that. But it was an attempt to get at the true perceptual independence between features, even within the same letter, say the probability of perceiving the horizontal and the vertical or the product of the two. When you go down to the micro level, you can look at the D prime given you detected the other feature or you didn't. And in theory, it should work perfectly well, but it turns out there's certain technical assumptions that are very, very strong about that. So it's not quite as robust. I still think it's worth developing. So now to go toward the more general theory, this stuff was all the backdrop for the original static general recognition theory. We were doing those experiments from the late 60s to the late 70s and early 80s. And Ashley and I began to develop a real theory, or meta theory, called general recognition theory that includes all of these former things. So let's now get a picture of it, and I think even without all the mathematics, you can see what's happening here. So suppose we have two psychological dimensions, x and y. These are, of course, some function of physical variables. So, for example, loudness should be mostly a function of intensity, and pitch mostly a function of frequency. But we already know those are not fully independent. Right? They're not fully, in fact, in our sense of a cross-stimulus invariance, they are not. But just to give you an example, so here are two distributions like little Napoleon hats, but then this is another depiction that's a lot easier to do, where you have the so-called equal likelihood contours. And therefore, we're still in the same space, the same idea, but we don't have to draw these Napoleon hats all the time. We can't go through all this, and there's no real need to. I'll give you the basic concepts in a more pictorial and intuitive way. So here we have the x and y dimensions, so these might be evidence for a vertical line or evidence for a horizontal line in one of these artificial alphabets that we did a lot of experiments with. So here would be the stimulus with capital letters, and here are the proper reports. So there's a one-to-one direct relationship between the stimulus and the correct report, although of course you could make confusions. Here's an example of a bivariate or two-dimensional situation with one distribution for each of the signal possibilities, each of the combinations of the values for the dimensions. No, I'm not stopping at 2 minutes, sorry. You talk to your boss over here. So here we have these lines are drawn orthogonal to one another at right angles, and notice that they're lined up in parallel with the perceptual axes. That's what we call decisional separability. And just as it turned out in simple signal detection theory that decisions were very, very important, and the psychophysicists in the 19th century did not understand that, it's even more important in multidimensional psychophysics. If these decision bounds look like this, so all that area upper quadrant is when you say A2, B2, you give that response. Down there you say A2, B1, and so forth. This decisional separability allows us to make extremely strong, draw conclusions about the underlying independence and invariance. If you don't have that, then it's much tougher. So again, I won't spend much time on this. I know mathematics makes some people sleepy anyway. But look at this joint. This is what I mean by the perception of the joint values on the two dimensions is the product of their separate values. So that's the truest kind of independence, the deepest kind of independence, and we call that perceptual independence. We grace that because it's the deepest kind of invariance. But there are other kinds that can have. Now this, you can test that partly by the sampling independence, and that's just a statement of that sampling or report independence that I told you about. Well, here are some kinds of perceptual independence or not. We can see that here we have perceptual independence, here we have perceptual independence. Here we have a positive correlation or positive dependence. Here you have a negative correlation or negative dependence. So that's the kind of thing we're testing from the previous slide. Okay. Now it turns out this is just a theorem that says that if you have those nice decision properties of the decision bounds, then our sampling independence or report independence gives us complete and perfect information about the underlying perceptual independence. So if we have this nice decisional property, Then the underneath is, you can tell exactly whether they're perceptually independent or whether they have some kind of correlation on those figures. Perceptual separability, I want to show you this again because we haven't much time. That this kind of invariance now, we just took that across stimulus invariance to a deeper level in terms of computational models. Okay. So now we see that we define perceptual separability, which is the same thing as the cross-stimulus invariance, if the marginal distribution, say on Y, is invariant across a change in X. Now, remember, that's what we meant by whether the feature was seen the same in either of the two stimuli. This is the way you're testing that at a deeper level, where you're assuming this underlying model. Okay? And our ways of testing it use the same observable variables as they did in this before we had the deep theory. But this just puts it. Notice here, you're not perceptually separable because the variance for one of the levels on the other dimension is much bigger than the first one. Okay? Here they are separable, here they're separable, the other ones are all separable. And yet this is just saying what I already said, so we can skip this or go real fast. This is showing the important concept of decisional separability, which can be tricky, a little trickier, unfortunately, to test, but it is possible. And this is just the observable. This is the cross-stimulus invariance. Nowadays it's known as marginal response invariance, but it's observable that you can test. Again, it turns out that if you have decisional separability, then you can draw really strong conclusions immediately about the cross-stimulus invariance. Here's a decision tree, an inference tree, showing that under what conditions you get various, draw various conclusions. So for example, I'll focus on the ones that we've just gone over. There is other stuff here, but we don't have time to do it. So if you have decisional separability and perceptual separability, then that implies the marginal response invariance. This stuff down here is observable. That's a test. Again, it doesn't depend on model parameters. Okay. Similarly, if you have decisional separability and that deep notion of perceptual independence, that is no correlation in those underlying distributions, then you imply sampling or recorded independence. Again, that's the observable. Then there's certain other kind of more refined notions that involve optimality and assuming normality of things. I've drawn all the pictures assuming normality, but the major theorems don't depend on local distributions at all. There's another way of testing this. It gives researchers a way of what to test and what kind of a flow diagram of getting this test and where do you go to make the next test. Don't have time to go through that. So here's an example of one of the few places where it turned out that you have strong independences. And that is with an alphabet that is made up only of these lines that are at right angles to each other. So your alphabet is composed of a blank, a vertical line, a horizontal line, or both together. By the way, it's very important to have what we call feature complete alphabet, because otherwise your decisional processes will skew what's going on internally. Okay, we can't explain that right now. But in this, we won't go through the details here, but basically the tests for the various kinds of independence and invariance will pass. As soon as you add one single feature, so now you've got 3 features, you've got a total alphabet of 8 possibilities, you lose independence of every kind, every single kind. And by the way, over and over again, we find a positive dependence in the sense of, in a more complex alphabet, if you perceive this one, then you're more likely to perceive another one. So it's a positive rather than an inhibitory. And that's it. And I almost made it. Thank you. Do we have time for questions? Everybody's not totally confused.
So, relax the question, Jazz. You said You mentioned that this decisional separability is independence, right? The decisional separability is independence. So you take it as an axiom system or not, or you just verify it by experiments, and you just mention in your abstracts.
Right.
So I'm just curious about that. Thank you.
Right. There are some tests for separability, but they're a bit more difficult. So what we can say is, from a philosophy of science point of view, is if you get sampling resistance, and if you get marginal responsive rates, like you get plus stimulus invariance, you can be very sure that you really have these. Because otherwise you would have some very strange kind of decision bounds interacting with your non-independence in order to produce something that looks like independence. On the other hand, if you do not get sampling independence or marginal response invariance, then you kind of have to shrug your shoulders. You don't know whether it was the lack of decisional separability or you truly don't have independence. There's one other item there that helps us, and that is we can also become more computational. And a great deal of work has been done by my colleagues and students over the last few years to go in and fit multidimensional Gaussian distributions to these. And if you have enough data, like maybe you have 3 dimensions instead of 2 and more levels and things like that, then you can get some real power for these more parametric models that also help us to test these solutions. Thank you. Very good question.
I was wondering if you think the same model could apply to identification of letters of different fonts, or maybe like Chinese characters, all kinds of different beautiful fonts that we still identify as the same character. And do you think that this kind of model can be applied to discriminate like same letters in different fonts?
Absolutely. I think it can be applied to really to anything. And when you have used it, for faces, face features, all kinds of things. So my colleagues will mostly be talking about SFP. Unfortunately, we don't have enough talks on the applications. So my last talk, I may try to do some applications because everybody else is talking about systems factorial technology instead of this. But yeah, you can apply it to anything. Now, your deepest conclusions may be drawn only after you also construct some artificial alphabets that look like Chinese characters, but don't come along with all the baggage that you have from the ones you use every day. Okay, but you can use both kinds of experiments. One was like my very first experiment was on the uppercase English alphabet, which is not featured because the letters has different features and things and stuff. But yeah, absolutely. And I should mention, as other people probably will, that you can use this along with other strategies. It just doesn't have to sit down by itself. So also bring it to bear. No? Okay, well, then I'm still going to sing my song.
One more.
No song.
Just a very general question. What is the feature? That is, do you really restrict to some sort of physical boundary as opposed to what if we say this is, would that be a common feature or is actually something going on?
Yeah, well, that's of course a very good question. It goes back way back in history as well as back in the first AI. So we still don't know what the real features are in language. However, that being said, that doesn't mean you can't learn a lot by manipulating physical variables that may or may not correspond. They correspond to something important. Exactly what the features are inside. That won't tell you, but it will tell you if the perceptual representatives of these physical things are varying, what their dependencies are. Now, without neurophysiology, and I hope for the day where we have enough convergence of evidence from behavior models and neurophysiology that we can draw extremely far. Right now, you're embarking on the deep issue of since I can take any feature dimension and I can transform it in an infinite number of ways, there are an infinite number of features you can be using. Right? But one thing we can do is look for ones, say, for parsing learning that show independence. Perhaps the neural system uses it, perhaps not, but it would be really nice to know about those. Right? Otherwise, some of them just have a kind of quote-unquote face validity that we have to take seriously. Things like pitch and loudness and so forth. They have so much psychological reality that we have to take those seriously. Others may be more ephemeral or we have to know that. Very good. Really excellent questions.
Any more questions? All right, let's thank STGRT.
Thank you for your participation. We will now take a 20 minutes coffee break. Refreshments are served outside. Enjoy the coffee break and please come back in 20 minutes.
谢谢各位的参与。从现在开始，我们有20分钟的茶叙时间。几位来宾可以到演讲厅外面的空间使用交换。请各位在10点30分时准时回到会场。感谢各位的配合。